Hello, my name is Brian Freno, and the title of my talk is Code Verification Techniques for Hypersonic Reacting Flows in Thermochemical Nonequilibrium. Hypersonic flows and their underlying aerothermochemical phenomena are important in the design and analysis of vehicles exiting and re-entering the atmosphere. Their high flow velocities and stagnation enthalpies induce chemical reactions and excite thermal energy modes. As a result, the aerodynamic and thermochemical models require full coupling. To model such flows, the Sandia Parallel Aerodynamics and Reentry Code, or SPARC, is being developed at Sandia National Laboratories. SPARC is a compressible computational fluid dynamics code that models transonic and hypersonic reacting turbulent flows. SPARC can also solve the transient heat equation and equations associated with decomposing and non-decomposing ablators, which are coupled to the fluid dynamics solver. Verification and validation are necessary to establish credibility of computational physics codes. Validation assesses how well the underlying models represent the physical phenomena and is typically performed by comparing computational results with experimental results. Verification, on the other hand, assesses the accuracy of the numerical solutions. Verification is typically broken into two categories: code verification and solution verification. Solution verification estimates the numerical error for a particular solution, whereas code verification verifies the correctness of the numerical method implementation. The focus of this work is on code verification. When the governing equations are numerically discretized, a discretization error is introduced into the solution. As the discretization is refined, the discretization error decreases. More rigorously, the discretization error should decrease at a certain rate. To compute the error, we use manufactured and exact solutions. Code verification has been demonstrated in many computational physics disciplines, ranging from fluid dynamics to electrodynamics to radiation hydrodynamics. For hypersonic flows, code verification techniques have been presented for a single species, perfect gas, and a multi-species gas in thermal equilibrium. Here, we present code verification techniques for hypersonic reacting flows in thermochemical nonequilibrium and demonstrate their effectiveness on the spatial discretization as well as the thermochemical source term. Our governing equations account for the conservation of mass, momentum, and energy. To account for multiple species, we include a density vector of each species' density such that the mixture density is the sum of the densities. We have the local time derivative, the convective flux gradient, the pressure flux gradient, the diffusive flux gradient, and the thermochemical source term, which is a function of the mass production rates per volume, the vibrational energies per mass, and the translational vibrational energy exchange. The mixture vibrational energy per mass is the density weighted average of the species' vibrational energies. Each of the energy modes is modeled by a Boltzmann distribution. The translational vibrational energy exchange is modeled by the Landau-Teller model, which is a density-weighted sum of the differences between the energy modes when evaluated at the translational and vibrational temperatures divided by a relaxation time. The relaxation time is modeled by an empirical formula. Finally, the mass production rates are expressed in terms of the forward and backward reaction rates and the stoichiometric coefficients. I'm showing these models not to thoroughly go over their details, but rather to convey how involved their structures are. The scope of this verification work is restricted to the non-diffusive flux gradients and the thermochemical source term. In particular, we are interested in the spatial discretization of the non-diffusive flux gradients and the construction of the thermochemical source term. Now, I will discuss the verification techniques for the spatial accuracy. On the left, we have the governing equations, and on the right, we have the discretized equations. The discretization error is the difference between the discrete solution and the actual solution. The truncation error is the difference between the discrete residual and the actual residual. Through some manipulation, we can show that when the residual is linear or linearized with respect to the solution, the residual of the discretization error is equal to the negative truncation error. For a pth order accurate discretization, the truncation and discretization errors can be modeled by a coefficient times h to the power p, where h is a relative characterization of cell sizes along one dimension. We can compute the order of accuracy from two meshes: a coarser mesh, characterized by mesh size h, and a finer mesh that is q times as fine as the first, characterized by a mesh size h divided by q. We can compute p by taking the logarithm of the ratio of the errors divided by the logarithm of the ratio of the mesh sizes. However, in order to know the error, we need to know the solution. We can use exact solutions. These require a negligible implementation effort since they satisfy the original equations, but these cases are extremely limited, and they only span a small subset of the application space. On the other hand, we can manufacture solutions. These won't satisfy the original equations, so they do require a source term. However, they can be manufactured to exercise features of interest. They should be smooth, continuously differentiable functions with generally non-zero derivatives and moderate variations. We could compute the order of accuracy at a single location in the domain, but doing so would be problematic. For cell-centered schemes, cell centers usually vary with mesh refinement, and in regions where the error vanishes, computing the order of accuracy is meaningless. Therefore, we use error norms to quantify the spatial accuracy. We can use the L1 norm, which gives us the average error. It is not significantly contaminated by localized deviations, such as those that can arise from discontinuities or lower order boundary conditions. And we can use the L infinity norm, which gives us the maximum error. The L infinity norm captures localized deviations, both the ones we expect and those that we don't. In the absence of discontinuities, both norms should yield the same order of accuracy. Now I will demonstrate the effectiveness of these approaches. The first case is a simple, one-dimensional supersonic flow case using a manufactured solution. The relevant boundary conditions are supersonic inflow and supersonic outflow. We consider 5 uniform meshes, and our manufactured solutions are sinusoidal perturbations to a uniform flow. The dashed lines in the plots, as well as the left half of the table, show the results from the original boundary condition implementation. In the left plot, which shows the L1 norm of the error is second order accurate. However, the L infinity norm shows in the right plot in the left half of the table that the error is only first order accurate. Upon correcting the boundary conditions, we were able to obtain second order accuracy in both norms. For our next case, we consider a two-dimensional domain which introduces a slip wall or a tangent flow boundary condition as an additional relevant boundary condition. We use 5 non-uniform meshes, and our manufactured solutions are again sinusoidal perturbations to a uniform flow. Here we see the values of the 4 non-zero flow variables. This slide is similar to what we saw previously. However, this time the reduction in accuracy from the lower order boundary conditions is propagated into the entire domain such that both norms indicate first order accuracy. Nonetheless, upon correcting the boundary conditions, we achieve second order accuracy in both norms. We now consider an exact solution, which is a two-dimensional steady isentropic vortex on a quarter annulus domain. For this case, we use 6 meshes. Here are the values of the 4 non-zero flow variables in Cartesian coordinates. From here on out, we will only look at the corrected boundary conditions and L infinity norm, which, as we can see, are second order accurate. Now we consider a 3-dimensional domain and 5 non-uniform meshes with manufactured solutions that are again sinusoidal perturbations to a uniform flow. Once again, we have second order accuracy. The previous results were for a single species flow. Now we switch to a 5-species flow consisting of N2, O2, NO, N, and O. These species can undergo 17 reactions involving dissociation and exchange. We return to the non-uniform two-dimensional mesh from earlier and manufacture solutions that are sinusoidal perturbations to a non-uniform flow. These are how the solutions look. For our first case, we consider a supersonic flow in thermal equilibrium. We can see the flow is second order accurate. Next, we consider a hypersonic flow in thermal non-equilibrium. Again, we can see the flow is second order accurate. Now we will discuss the thermochemical source term. The thermochemical source term is algebraic. Therefore, it is computed the same way on both sides of the equation if we use manufactured solutions. And as a result, manufactured solutions will not detect implementation errors. We are therefore going to compute the translational vibrational energy exchange, the vibrational energies, and the mass production rates for a single cell mesh with no velocity, for many values of the species densities and the two temperatures. We're going to compare the values with an independently developed code, and we're going to perform convergence studies on the distribution of the values and the relative differences. The relative differences are going to be computed symmetrically at each query. At first, it may be instinctive to dismiss this as a typical code-to-code comparison, which usually lacks rigor. However, this approach has several distinctive and rigorous features. First of all, the independent code is developed internally. It uses the same models and material properties expected from SPARC. The models and properties are taken directly from the original references. On the other hand, with external software, assessing the implementation is non-trivial. The wide variety of models and properties complicates quantifying agreement, and we have less control over the precision of the output. For our purposes, we require the relative differences to be low, as in near machine precision, because the models and material properties are the same. Code-to-code comparison, on the other hand, is typically content with agreement within a few percent. Also, our approach has a wide condition coverage. We query the comparison for thousands of conditions spanning extreme ranges. Code-to-code comparison typically considers only a single or few conditions. Now we will look at the results for the thermochemical source term. We begin by specifying ranges and spacings for the dependent variables and examine how the minimum, mean, and maximum of the absolute values of the variables of interest converge with respect to the number of samples. Since we're using Latin hypercube sampling, the sample locations for each amount of samples are independent. We can see that the minimum, mean, and maximum roughly converge. For our maximum amount of samples, which is 131,072, here are how the quantities vary. As you can see, they span at least 16 orders of magnitude. Now we're going to look at the non-zero relative differences between the translational vibrational energy exchange and the vibrational energies. We were expecting agreement near machine precision, but this is clearly not the case. Delta QTV is greater than 10% for about 9% of the simulations, and greater than 1% for nearly a third of the simulations. Additionally, the relative difference in EV is greater than 100% for some simulations. We discovered that these discrepancies were due to two causes. The first was incorrect lookup tables for some of the vibrational constants. These introduced errors in QTV for all simulations, and the implications could be seen in realistic simulations. The second cause was loose convergence criteria when computing the vibrational temperature from the vibrational energy. These criteria were unsuitable for low values of TV and introduced errors for all variables for some simulations. For a converged steady problem, however, the original criteria would be acceptable. Now we compare the original relative differences with those that arise from correcting SPARC. These relative differences are consistent with our expectations. For QTV, they are less than 10 to the negative 10 for all simulations, and for EV, they are less than 10 to the negative 14 for all simulations. The relative differences in QTV are greater than 10 to the negative 12 for only 48 out of the 131,000 simulations. This happens when the translational and vibrational temperatures have a relative difference of less than 0.2%. When this happens, the energy modes in the numerator of QTV share many leading digits, such that when they are subtracted, there is a precision loss. Regarding the mass production rates, the before and after cases are very similar. Both are consistent with our expectations. The relative differences are less than 10 to the negative 9 for all simulations. And of the more than 600,000 computed values, only 109 have relative differences greater than 10 to the negative 12. This is due to the precision loss that can occur from the subtraction in the mass production calculation. Finally, we compare the convergence histories of the maximum relative differences before and after with respect to the number of samples. The discrepancies in QTV were immediately evident, whereas for EV, the discrepancies weren't evident until we used 64 samples. To summarize, the manufactured and exact solutions were effective approaches for verifying the spatial accuracy. They detected multiple issues. Additionally, the L-infinity norm proved to be more revealing than the L1 norm. However, these approaches are insufficient for algebraic source terms. Therefore, we introduced an approach for verifying the algebraic thermochemical source term. It detected multiple issues, and we saw the importance of performing a convergence study to ensure the samples were sufficiently representative. If you would like to read more about our approaches, you can in our article that is being published in the Journal of Computational Physics. You can also access it on arXiv. Thank you for listening to my presentation.